Hello everybody and welcome back to MI212. This is Mark Gastonguay and this is our lab session today on the topic of advanced PKPD modeling part 1. And more specifically we're going to be talking about indirect response models and direct PKPD relationships. You'll notice from the course website that I've posted an example set. I did that earlier today. This is for demo purposes only. And as I had indicated earlier in the course, this is a review of material that was presented in MI210, just to make sure that we're all at the same basic level before moving to the more advanced PKPD topics in week 7 and week 8. But if you'd like to follow along today, those examples are there, or go back and reproduce those results on your own later. In that examples folder, I've just blown up here to show you that there are several files included, and they include code examples for all of the models that we discussed in lecture last time. That includes the direct PKPD models, as well as the different implementations of the effect compartment, either using the analytical multi-compartmental ADVAN, or the more general linear models such as ADVAN 5 or 7, or full differential equation models. In addition to that, we have each of the 4 indirect response PD models, and of course the tolerance model that we discussed. There is the non-parametric PKPD model that we discussed. There's the non-parametric PKPD model that we discussed also. On top of that, there are a couple other examples that I've thrown in there. One is a model for warfarin pharmacodynamics, and another one is a tumor growth using a Gompertz model. So all of those will be in the examples folder that you can download as a zip file from the course site. For the problem that we're working on today, we're just going to use model 1 and 2, which are a direct PKPD model, as well as an effect compartment using the analytical ADVAN. Okay, so you can find that on your week 6 lecture materials. Let me also remind you too that we have an assignment for the coming weeks. There are 3 or 4 papers identified in that assignment. You don't have to read them all before Tuesday, but they will be useful reading material as background for the next 2 weeks. So when you go to SIMI with your new zip file for the Advanced PKPD 1 lecture, and you unzip it, you'll create a subdirectory such as this, ADV PKPD 1. Like I said, there are many examples here that we're not going to run through in class, but we'll do the first 2 to show you this analysis of a data set called PKPD.CSV. And you'll notice I've included that data set as PKPD.CSV. There's also another one here called PKPD indirect.CSV. It's actually the same type of data set, but the second one here called indirect is mocked up to allow for initialization of an indirect pharmacodynamic response compartment via a dosing record. And so let's take a look at both of these before we get started. So the PKPD data set, let me increase the font for you. We have our usual comment column, ID, amount, time, dependent variable, a type indicator for PK versus PD, and a compartment indicator in case we want to use an effect compartment model where 1 is the depot, 2 is the central compartment, and 3 is the effect compartment. There's a PK dosing record, and then we have observations following. The indirect response code is similar, but now we have 2 dose records. So you'll see the first record here is a dose of 500, and that's the dose of drug in the PK system model. And then we have a dose of 1, which initializes compartment 3. So this is the trick that we're using to initialize the pharmacodynamic indirect response compartment. Remember I showed you in class how with NONMEM 6 and 7 now we can use the A0 parameter to initialize the initial amounts in the differential equations, and that could be used instead of this dummy data record. In fact, it's doing a very similar thing, but behind the scenes, and does not require modification of the data set. So if you want to try that indirect pharmacodynamic response model, use this data set, which is called PKPD indirect, if you're going to use the strategy where we insert a dummy dose record with a unit dose of 1 to initialize the compartment. Or if you are going to use the A0 parameter in the control stream, then you can just use the PKPD data set that doesn't have those additional data records. Otherwise, these two data sets are the same. But today we're going to actually run a direct model on this data set and an effect compartment model just to compare those differences. So let's take a look at our first model is a PKPD system model. So this is 1.ctl, and I'll pull it up in the browser. We've got the usual setup here, but we're going to use Advan2 trans 2. This is a one compartment pharmacokinetic model. We have some prior knowledge, imagine, about that. And we're going to have a direct link of pharmacodynamics to the central compartment concentration. The data set doesn't require a compartment data item. In fact, you see here the word drop has been used instead. This is the PKPD data set that we just looked at. So we have ID, amount, time, dependent variable, and type, where type is 0 for PK and 1 for PD. So in the PK block, it's the same old story. Our required PK parameters, Ka, clearance, and volume, and we're scaling on the central compartment here. The error block is where we define the pharmacodynamic model. We'll propose an Emax model, in this case Emax, EC50, and E0. And so then we have an effect prediction that is E0, the intercept, plus the Emax model, Emax times F divided by EC50 plus F, where F in this case is the prediction from the PredP subroutine in the default compartment. In this case, it's just a central compartment. It's a direct response. And at whatever time the observation is made. And then we have an additive residual error term. Concentration is described by some prediction of concentration F and a proportional residual error. And we use the type indicator variable to switch between effect or concentration predictions depending upon what type of observation each data record is. So that's pretty straightforward. The rest is as we would typically do. This is a direct population PKPD model. Let's see what happens when we run this. So there's an R script called advpkpd1.r, and we'll open that in an editor. And I'm also going to open up an R window. Okay, so let's look at the script window. The usual functions are required. Let me make this a little bit bigger. Okay. The usual libraries need to be loaded. MIfuns, of course, that's the function we're using. And the lattice library for plotting. So we can evaluate those. And those are loaded. Set up the project directory. Again, this is the MI212 ADV PKPD1 lecture. And then your nonmem run command, we're going to use the same nonmem installation for every one of these runs, so we'll just define it once. Okay, so our first run here using the nonr command is our direct PKPD model. We can use the features of nonr to separate out the two types of variables. So we're going to use the type variable here to group our output plots, and the group names we're going to just call one. And the way that type works too is it always sorts according to level. So 0 is the first and 1 is the second. So 0 is PK, 1 is PD. And we're going to include the individual ADAs here for plotting. And we'll evaluate that one. So compile now, and it's going to execute while that's running here. Let me answer a question or two. So the question, during the model building process, how do you determine the Hill coefficient? When to fix at 1 and when to estimate? Well, the most flexible model, if we're talking about a full sigmoid Emax with a Hill coefficient, is one where you estimate that parameter. And I guess, to be thorough, you would just try that initially with all models. You might get some sense from looking at the concentration and response data. If you had rich enough data within the subject, you might be able to see some of that sigmoidicity, but the only real way to determine that is by estimating it. So throw the parameter in the model and estimate it, see what happens. If the estimate ends up to be very close to 1, or if it's just really poorly defined, huge standard error, that probably means that that you can do without that parameter. But to really answer that question, you have to estimate it to see what happens. In a direct model, is F always the concentration here, unlike some of the other models? Yeah, let's go back to that code for a moment. The nice thing about the direct model is that we don't have to keep track of different compartments for the concentration prediction versus the effect prediction. All predictions are being driven by the same compartment concentration. So F here describes that concentration in the default observation compartment, and that's what's actually used in both cases. Now, that doesn't stop you from going in and inserting a couple of lines saying, CP equals A2 divided by V2, or A2 divided by V in this model. And then just specifying your model, concentration equals CP plus CP times 0.1. And then effect, though, would still be driven off of the same CP. So you'd say E0 plus Emax times CP divided by EC50 plus CP. So that, you can define it yourself, or you can use F, which is the predicted concentration coming out of the pred-PP subroutine. In the direct model, it doesn't really, there's nothing to be confused by here because there's only one compartment involved. So you can save yourself some typing, just use F. Okay, here's the run. It looks like it completed. Let's see what happened. I'm just going to refresh here. And there's our run subdirectory 1, and let's look at the output file. That's where I usually start. This just echoes back the model that we ran. Remember, in class here, we're running the FO method with post hoc just for runtime purposes. So here's what we want to look at here. Monitoring of search. We have initial objective function value of 5600. It gets minimized down to 1600. You see that the gradients here starting off kind of large, and we haven't actually called for more than just the initial and final iterations, but you see at the end they're all substantially smaller and there are no zero gradients. To do a thorough evaluation of this, we'd want to use the option to print the gradients more frequently, and that's specified on the estimation line. You could say print equals 5. That would give you iterations listed every 5 iterations. Okay, so everything looks okay from here. I don't know what the final parameter estimates are supposed to be, but we've minimized. Looks like all the parameters are pretty well behaved. We've got nothing blowing up or approaching zero on the boundary, so looks okay. Let's look at diagnostics. Here's diagnostic plot review by type. So the first type we're going to look at is PK. Population and individual observed and predicted. And you see on the left side here the population predictions. We see some heteroscedastic variability, but pretty well centered around zero. A couple of individuals that look a little bit odd, but not too bad. See the proportional nature of the variability and weighted residuals corrects some of that. There's a little bit of bias there. I might want to look at a more thorough estimation method here before agreeing on this PK model. But then we go to the residuals and weighted residuals, and we see some bias here. What we see even worse, though, when we go to pharmacodynamics, is that now the population prediction is severely off. We have many of these values here with high predictions and low observations off of this unit line, indicating a biased fit. Although when you go to the IPRED, it seems to correct it a bit, but that's just because the individual ETAs are essentially soaking up that difference and making a better prediction. It's camouflaging the fact that we have a structural model problem. It's really clear here on the residuals versus prediction, and weighted residuals also show some problems, and you also see that problem versus time. So even though this converged, these diagnostic plots are not something we'd be happy with. Individual ETA scatter plots, well, looks okay, but you can see down here, look at ETA1, it almost looks like there's two populations here, two clusters of solutions for that, and same thing with ETA4 here too, bouncing back and forth. So, you know, you might think of something like, oh, maybe there's a mixture model involved and so on, but let's think of the first principles first. We need to understand our PKPD system. So not such a good fit here, not such a good fit with a direct model. So of course, what we would want to know is, well, what does the relationship really look like, and do we have enough data to understand that? So let's go back to the R script. What I've done here is just a real simple step where we're going to do some graphing, pulling in the output from the first run, or I could have pulled in the data set to do this piece. We'll run that. We're going to create a PDF graphic, and it's just a simple plot of the observation versus time conditioned by type. So we're just going to look to see what happens to the time course of concentration and the time course of response. Okay, and device is off, so graphics have been created. Let's go back. Here's the PKPD plot we just created. Oops. And so a couple things we can notice here. First, type 0 is PK, type 1 is PD, so it's PK on the left, PD on the right. The time scales are the same here. We have 50 hours in this study. Unfortunately, we're putting them all into the same y-axis here, but we can still, for a quick plot, we can just still make some inferences. Look at the concentration response curve. It peaks pretty rapidly here with a Tmax at about, I don't know, just guess a couple hours maybe, and then decays over time. However, when we look at the response time relationship here, we do see a rising and falling of response, but it's certainly not within the same time course as the concentration curve. In fact, it rises up here, probably peaks somewhat after 10 hours, and then starts to decay. So right there, that tells us that there is not a direct relationship between these two. When the pharmacodynamic response is peaking much later than the pharmacokinetic response, you know that there can't be a one-to-one relationship between PK and PD. And so this alone would force us to look at indirect models, starting with an effect compartment. You know, some of the other things you can do, and we talked about this in the 210 class, so I'm not going to belabor the point, but we can plot and look at hysteresis loops by individual. We can look at relationships of superimposed concentration and response for each individual versus time. These are the kinds of plots you'd want to create. But if you see that sort of relationship, you know right away, you don't have to even look at an objective function. You know that a direct model is not appropriate for this data set. So now the question is, well, which of the indirect relationships should we use? And if you have a strong mechanistic reason and you know that there's an indirect pharmacodynamic response mechanism involved, you might move to one of those models. But as a starting point, I think we just go to something simple like an effect compartment model that allows us to describe the delay in the response versus time. So that's what we're going to do next. This is 2.ctl. It's an effect compartment population PKPD model. We have all the same data items, but now, remember before I had used drop to ignore that last column. Now we're going to label it compartment, CMT. This means something to NMTran. It's going to assign the event in each compartment. So compartment 1 will be the doses into the guts. Compartment 2 will be the plasma drug concentrations, and compartment 3 will be the response observations. Same data set and same PK block. Now what we're going to do though is we're going to use advan4 because we're going to take advantage of the analytical solution of that 2-compartment PK system to model a 1-compartment PK system with an effect compartment. And so we have a Ka clearance and a volume. We're going to estimate the first order rate constant for the equilibrium half-life here, the Ke0, specifying everything back into microconstants because remember this is trans 1, so we're required to specify every microconstant here. K23 is the transfer from the central to the effect compartment, and we want that to be a negligible mass transfer. That's why we multiply it by 1/1000th of the elimination rate constant. K32 is actually the Ke0, which is an estimated parameter. And remember this equality here so that we set up the intercompartmental fluxes to be the same. That allows us to interpret the concentration in the effect compartment on the same order of magnitude, the same scale as the plasma concentrations. Now, like I showed you before, we can define the CE and CP here, or since we're using the compartment item, we can rely on F in our model. So either one would be useful here. Emax, EC50, and E0 we're defining again with fixed and random effect parameters. The concentration prediction is equal to F times this exponential error. Remember that F takes on a different value depending on what type of observation record. So if you use F here, be careful because if the record is a PD response record, we're still going to predict something called concentration, but it's going to be a different concentration. It's going to be a concentration in the effect compartment. Okay, and of course we're not going to use that to compare to the observed data. But F here takes on a different prediction now depending upon what the observation record says. So this might be a case where it might be a little less confusing or explicit to use CP here in this model and to use CE in the effect model, although the current construct is perfectly fine. It's just you've got to be careful and you've got to be paying attention to what the CMT data item says. Now let's say you wanted the concentration and the effect prediction at every data record. Okay, so let's say data record 1 is a concentration prediction, but we want the predicted effect and the concentration at that record. Well, in that case, you can't use F. In that case, you have to be specific about the compartment you're calling because F, remember, is always going to be determined by the compartment data item whereas we can override that by selecting the specific compartment we want. So just keep that in mind. Probably a good habit to just define these explicitly and use the explicit compartment concentrations. Okay. A question here about the residual error model. Let me take a minute to answer that while we have the code. What's the difference of the exponential error model? Is that equivalent to an additive model in the log domain? Well, you might think so. So we have here an exponential residual on concentration. It looks like it's the equivalent of a log transform both sides, but it's not. And that's because of the first order approximation that's made in NONMEM. If you simulate a NONMEM with this model, there's no first order approximation made, and you do get a true exponential simulation. But when we estimate, this collapses down due to the first order approximation to a proportional residual model. If you want a true exponential residual, you've got to use the log transform both sides approach. Okay. So that's the code. Let's go back to where we were now. We'll run number 2. Again, the setup is the same as always. We're going to change the run number here. The types are the same. We haven't changed the structure of the random effects, so we're going to keep all of that the same. And we'll just execute this block. And while it's running, if there are any more questions, I'll answer those. Okay, so plotting is complete now. Let's go back and take a look. Diagnostic plots by type for run 2. Now it looks a bit better, doesn't it? The population and individual observed predicted plots are much cleaner for the PK records than they were before. So one thing that we noticed in this model, when we ran the direct model in a simultaneous fit, and this is one of the potential challenges in simultaneous fit, is that we actually had some misspecification in the pharmacodynamic side coming back to impact the PK fit. Right? If we compare these diagnostics to the prior run, the PK is much better here. So that is another potential argument for moving forward with a sequential fit where you fix the pharmacokinetic data to the individual estimates. At least when you're exploring the particular pharmacodynamic model structure or even the link structure, it might make sense to anchor down the PK to something that you're confident in. So as you see, and in fact, I'll pull it up side by side here so that we can compare them. So it's not just from memory. The right side is the direct model. The left side is the indirect or the effect compartment model. And this is the pharmacokinetic data we're looking at here. You see the goodness of fit is much better on the left side, even though all we've done is we've changed the way that the PKPD response is linked to PK. It's a good example of misspecification in pharmacodynamics feeding back to alter your PK estimation. Okay, but now we've got an improved picture because we've actually dealt with the PD data a little more appropriately. Look at these side by side. So you can see the bias that was evident before is gone now in the PK side. Residuals versus time looks a little bit better as well in the current plot. Let's look at the pharmacodynamic endpoint. And this is where you see a really big improvement. This large biased misspecification here is completely gone now in the population observed predicted. And when you go to the individual level, even tighter than before. So we see in this, from just looking at diagnostics, that this is clearly an improved goodness of fit. Let's look at residuals versus prediction and weighted residuals versus prediction. Remember that we proposed an additive model. If you look at the pattern of residuals versus prediction, on the right side with the old model, it's really hard to tell what the shape of the variability of the data should be. But on the left side, where we have a model that's not misspecified, you see a nice constant band of residual variability. And of course, with an additive model, the weighted residual is going to look just like the residual, except for the fact it's accommodating the inter-individual variance as well. So much better diagnostics on the left side here. The effect compartment model. You see it here versus time too. And this is one place where a diagnostic versus time is very handy, is when you are looking at a model that allows for that kinetic lag, you're going to see bias versus time if that's not incorporated correctly. So pretty clear. You can see it here too. Even nicer distribution of the weighted residuals. Individual eta scatter plots now. Some of those clusters that we saw on the right side are not there anymore. Looks like we might have some need for covariance terms here, maybe like eta 6 and eta 3. This is nice in that we have now a mechanism to allow for random correlation between PK random effects and PD random effects. So if there happens to be a random correlation between EC50 and clearance, for example, you could accommodate that. And that's only available when you do a simultaneous fit. Eta distributions. Remember, we've got a small data set here, so it's hard to tell, but still doesn't look perfect on the left side. Let's go to the density plots. Those are a little bit cleaner. You still have some multimodal issues here, but a little bit better on the left side than the right. Yeah, probably need more individuals, and I would also, again, run a conditional estimation method when it comes to estimating individual random effects. Okay, so several questions have popped up here. Let's take a minute to answer those. In the effect compartment model, compartment 3 is the drug concentration in the effect compartment, and it's not the PD effect, question mark. That's correct. In the effect compartment model, compartment 3 represents a hypothetical effect compartment concentration, which then enters a PD model, and such as an Emax relationship, and is converted to a response. Okay. However, in the expression, and then they're identifying the residual model for effect. Effect is obviously a PD endpoint. A little confused. Okay, so let me go back and see if I can explain that. Let's take the code for 2.ctl, and we'll focus right in on that section. Remember, we're using a compartment data item here, which is going to define which compartment a particular response is associated with. Go down to $error. We're going to define two predictions, one for concentration and one for effect. Concentration is just equal to the F. That's the observed value. And we're only going to use it to predict concentration when the type is equal to 0, which is a PK observation. And when type is equal to 0, that's when compartment is equal to 2. And in other words, concentration is the prediction of the central compartment concentration. So concentration is directly equal to F. Well, effect is not directly equal to F. Effect is related to F through this Emax expression, right? So that's the pharmacodynamic model. The predictor in that pharmacodynamic model is F. And in this model, F on a pharmacodynamic record, where type is 2, that's associated with compartment 3. Compartment is 3 when type is 2. And so that is the prediction of concentration in the effect compartment. So effect is not equal to F. Effect is equal to some transformation of F, where that transformation is an Emax model. And F in that case for the prediction is the predicted concentration in the effect compartment. Maybe it'd be simpler if I had just used CE and CP here to denote the two compartments, but it works either way if you have the correct specification on the CMT data item. Okay, another question. Out of curiosity, is this real data or simulated? Well, of course, all the examples we use in the class are simulated, but they come from models that we've come across in the past. So the design might be a bit cleaner than real data, but it's not too far from reality for, let's say, a simple phase 1 study with a simple PD biomarker. Okay, question about variability in clearance. We always say inter-individual variability of clearance is 30%, which means omega squared is 0.09, or the variance of eta is 0.09. But why all to be CV% of clearance? Okay. I think there's some confusion in this question about what a constant coefficient of variation means. What we're specifying here in the inter-individual random effects, in fact, we're specifying initial estimate of 0.04. That's a variance that corresponds to a standard deviation of 0.2, and when we look at that, that's a 20%, a 20% coefficient of variation. We could probably take that discussion offline. This is covered extensively in the 210 class also. Okay, any further questions on these two examples? Now, I didn't do it, but another plot that you might want to create is to capture, plug in CE and CP here, and then capture CE in the data set, and then plot, your CE, or the effect versus CE side by side with another plot that would be effect versus CP, and you'll see that what happens is the hysteresis that's evident under the plasma concentration observation should be collapsed and shrunken down to a single monotonic relationship for the effect compartment concentration versus response. Anyway, that's the basic idea. You can try this same data set with one of the indirect pharmacodynamic response models. And we have this lagged response where you have a rising in response and then a lowering response. You could do that by either stimulating the zero order K in or by inhibiting the first order K out. So you could try either one of those models as well. There are examples for each one of those here. They're just written in basic NM-tran. They don't necessarily follow all the conventions you need for non-R and MIfuns, so pay attention to that. But the basic code is there. All right, so that's the review of PKPD models. We're going to extend these. We're going to work with differential equation models in more detail in the coming weeks, talking about precursor pool models, models for multiple endpoints, models for lifespan or transit compartments and so on to describe hemopoietic systems, for example. Anyway, it's all based on these same basics. Okay, a couple more questions have come up here. Let me get those. In the one line, we have concentration equals F times E air. Okay, so back to the code here. This line is what we're talking about here. Concentration equals F times E to error 1. For compartment 3, will this be CP or CE? Well, it will be CE. It'll be the effect compartment concentration. So this concentration prediction is not a prediction. It's not valid when you're on a PD record. Okay, but that's okay because we're not trying to make a prediction of concentration on a PD record. So you've got to make sure to match up the type of record with the observation type. Now, if we had used CP in here where we defined it, then that's correct no matter what type of observation you're looking at. And if we use CE here, that's correct always. Doesn't matter what kind of observation. It's just that F will flip back and forth depending upon the compartment type. Okay, sorry for if that's confusing, but it's one of the flexibilities of the tool, I guess, and you just have to keep that straight. Okay, when type is 1, the DV item is always corresponding to compartment 3. It seems like DV is PK in compartment 3. How can this become a PD? I don't think that's correct. We'll have to look at the data set there. When type is 1, the DV item is always corresponding to compartment 3. That's right. Type 1 is PK here. Type 1 is PD. So type 1 should correspond to a PD. And if you go down here, type 1, if you put type equal 1 here, what happens is the concentration drops out and effect comes on. So when type is 1, the DV is compartment 3, and that's pharmacodynamics. It's not PK. Okay, so it's correct. You just have to realize which one of these predictions is going to drop out. When it's type 1, effect stays in the model and concentration drops out. When it's type 0, effect drops out and concentration stays in. Are we assuming that CE has similar error as CP? Well, no, not necessarily, because remember, we haven't observed CE. There's no error. We haven't observed it. There's only a residual error where you have an observation. So the only residuals we need to specify are the residuals on the measured entities, and that's plasma concentration and response here. So we're not making any assumption about the error in the CE. And in fact, when we predict it here, we're assuming we know it without error. So this F in this compartment there's no residual attached to that. That's just individual specific prediction of the effect compartment concentration. Okay, but is compartment 3 the effect compartment, the PK effect compartment? Compartment 3 is the effect compartment. There's a question, I think you're confusing two things. There's no PK effect compartment. Compartment 3 is an effect compartment. Compartment 2 is the PK observation compartment. So let's not confuse the two. There is no PK observed in compartment 3. Compartment 3 is just a hypothetical compartment that allows us to display that distributional disequilibrium to describe a lag in pharmacodynamics relative to pharmacokinetics. All right, lots of good questions there. I would suggest that some of you who might not be so familiar with PKPD models to read some of the reference material that we've provided. It'll help you understand what's necessary for some of these derivations of effect compartment models and indirect response models. Okay. Well, in the few minutes we have remaining, I thought that I would catch up a bit on some of the thread of questions on the discussion board. This class has been very active with questions and comments, and I have to admit that I can't keep up during the week with my other responsibilities here. So I'll try to take some time right now to catch up on some of those. Bear with me if you've posted things and I haven't gotten to them yet. It's not intentional. It's just you're asking a lot of questions, and I'll get to them when I can. But let's see if we can catch up on most of these here. I'll go to the forum and discussion. And I'll just start at the top here. Let's see. So how do I modify the code to apply it for log transform data? And it looks like Ganesh has already volunteered, and Jun have also volunteered some responses here. Yeah, so of course you've got to log transform the LOQ. You've got to log transform the prediction, right? The other piece here, though, is that you're going to have to convert your residual model. So moving to log transform data, you're assuming a proportional residual here. Well, that's going to be approximately the same as an additive. So you'd want to lose this proportional relationship here, and you'd just make it an additive type relationship. In addition, if we're going to use this density function, we want to use the density function that adjusts for the fact that actually this one's fine. This is the method, the M3 method, which allows data to range from anywhere from negative infinity to positive infinity, which is the case with log transform data. The log transform dV is going to be anywhere on that scale. So a few things you need to do. Number one, you need to, as suggested here, log transform the LOQ, log transform the prediction. I would drop, you have to log transform the prediction here, but I would drop the proportional component as been suggested in this thread, where sigma 1 times error, and error 1 is fixed to a value of 1 here. This is the residual error on the log scale now, and it's approximately a log normal error, versus up here where you have written a proportional. So actually this one's already been answered by the class. Thanks, folks. Let's move on to the next. Circadian baseline, I think I already answered that one. Simultaneous data, yeah, I answered that one too. Problems for advanced PKPD, advanced PK2, yeah, those are posted on the web now. Is this the same question as before? Let's see. Trying to use some of my own data using M3 as taught in the course. I previously used M6. I want to try something more robust. I'm having problems with a Hessian of posterior density that's non-positive definite during the search. As soon as NONMEM started, it suggested this might be caused by including time records that are 0. That's right, but I can't find any incidents of this. My control stream is pasted below. Well, let's take a look here at the control stream. I haven't run the model, but you've got a input data subroutine advan 9. It's a differential equation model. We have a central, a peripheral, and a peripheral. You could run this in advan. This is a 3-compartment model. You could run it in advan 11, which is an analytical solution, but that's not going to necessarily solve your current problem. So you have your PK parameters defined, your microconstants. I see here. Now you've got some lag times defined. Yeah, so this might be the cause of your trouble. Having a 0 record is essentially the same as having observations that are being made that are earlier than the lag time. Because of course there's going to be 0 prediction at that time point. One of the difficult things with NONMEM here is to estimate inter-individual variability in lag times. So alag1, I would just look at alag1 as a single population mean effect with eta 7 fixed to 0. I've never been very successful in trying to estimate inter-individual variability in a lag time. If you need to do that sort of thing, you might be better off with a series of transit compartments. Lag time is a very difficult parameter to estimate in these models because it's a discontinuity in the system, and when we throw the random effect on there, it just causes all kinds of trouble. So that's probably what's causing the issue here. I'm trying to understand what you're doing here. If dur equals 10, well, duration is an estimated parameter in the model. You have rate. Yeah, so you're, but depending upon the duration of the input, you're asking the lag to take on a different value. It's an interesting model to pose. There's probably a reason for that. And I don't think that that's the problem here, but what might be the problem is the random effect on the lag time. What you might want to do is just get this model running even without a lag time. You know, just assume that it all starts at 0, then add a simple lag with a population mean effect only. If you need more individualization, then go to a transit compartment model. Okay, that's what I would try there. Let's see, where were we? Tolerance modeling. Oh yeah, I already answered this one. BLQ. We want to use a simple approach to estimate when there are BLQs, either because there are a few or because there are problems with the M3 approach. Which simple method is preferable? Is it the Shiner method, where we delete the first of each? We delete all but the first and set the remaining first values to dv over equal to LQ over 2. Use additive plus proportional error model with fixing that problem. Yeah, I'm familiar with this approach. You know, there's controversy out there. Some people will say use this method. If you're going to use a simple approach, I just would use the approach where you drop all of the BLQ records and you don't impute them with anything. You just comment them out of your data set and fit the model as if those data were not even there. If it's a small fraction of data points, that's just about as robust. And Stuart Beal had published in his first paper on this topic some of the performances of those, and that method didn't do too bad if the variability was, if the missing fraction of due to BQL was not more than 10 to 15%. So that's the simple approach that I would use, is just comment them out. It doesn't require much playing around with the data, and it's pretty straightforward. You can go back to that Beal paper, ways to fit models when you have data below the quantitation limits, in PKPD, I think 2001. We referenced it in the lecture. That shows some comparative performance there. But that's a simple way to do it, and I think that's where I would go. Okay, time for a few more. Let's see, questions on parent-metabolite. I understand not wanting to have urine results correlated with plasma results, different physical samples, but as long as it did not include them in the same sigma block, does it matter if I have plasma and urine records in an individual with the same L2 value? I see. So if you use the L2 indicator to correlate them, but you don't allow that structure to estimate them, what happens? Yeah, I think that's going to be fine. You're not going to be able to estimate that covariance. I would probably, just to be explicit, I haven't compared what happens, but I would be explicit all the way here and identify that those are not L2 correlated items, and I would use a different L2 item for the urine values. But I'm guessing that if you don't, it's still going to be the same. I have not tried that. So if you don't model the correlation, but you have the L2 there, that's the same thing as not having the L2 there. That's my guess. Somebody's going to have to try that and replicate it. Number 2, I noticed that ALAG was included in the model when the plasma was alone, but ALAG was not included when the plasma was fitted together with urine data. Could this have caused some difference between results for the two models, hitting boundaries and gradients? Yeah, it could be. It could cause some differences. I did not notice that. It could also be that the ALAG, when we were fitting the data alone, was close to 0, and we decided to just drop it for the next run. But if it's non-zero, it could certainly, it's a different model, so it could lead to some differences in gradients. Yep. Okay, let's go back. Target mediated problem. Oh, just answered that one. Sorry. Nathaniel responded about target mediated, and that was just a correction to the code, so I'll skip that one. Interpretation of fixed volume. I've always struggled with this one. How do we interpret our results when we fix the volume of distribution of the metabolite? And this is for the parent metabolite model that's unidentifiable unless you fix VMet or F converted. My understanding is what we really estimate is an FMet that is some function of our true VMet. And so our estimate of clearance of the metabolite is really CLM over F times FMet true in the case of oral. And then CFMet is FMet estimated times VMet true. Then how do we interpret the elimination rate constant of the metabolite? Well, I agree with everything you wrote up to here. I have to think about what you're talking about, the elimination rate constant of the metabolite. First of all, we probably want to estimate the clearance of the metabolite. And so the clearance of the metabolite is also relative to the oral fraction as well as the fraction metabolized. So the clearance of metabolite, I wouldn't view it in terms of a rate constant. Clearance of metabolite is interpreted with the same caveats that clearance of okay, I get the question now. I thought you were interpreting clearance of parent and clearance of metabolite. Yeah, clearance of metabolite is here. How do we interpret the elimination rate constant? Why do you want to interpret the elimination rate constant? I think what really matters here is clearance and volume. Elimination rate constant is just a proportionality constant. Yeah, I agree in your interpretation of the clearance of the metabolite and the volume of the metabolite. I would not worry about interpretation of the rate constant. It's not a useful parameter to interpret. Okay, next question. Probably got time for one more here. Target media interpretation, fixed met versus fixed volume. You know, the best way to deal with parameter identifiability is to fix the fraction metabolized to 1 or to some known value if you knew that. However, there are instances in which that might not be ideal. I'm thinking about the lines of polymorphic enzymes in which you expect differences in the values of FMet, and literature values are not available. That's a good possibility there. So where F metabolized is not a constant, it differs between individuals. What you could do is you could set this up as a mixture model now, where you still fix to some population level fraction metabolized, but based on some known genotype and so on. I guess what you're asking here is if you don't have the genotypic information, you know it's a polymorphic distribution, and so fixing it to a single population value might severely bias some of your estimates. And I guess you're just in a difficult boat there. Even by fixing the volume of metabolite, you're going to run into trouble there too, because it's that amount being transferred that's going to be variable here. I think you need to find that covariate in this case. Interpretation is always going to be confounded between potential polymorphic differences as well as whatever you fix that fraction metabolized to. That's a difficult one to solve. Get the covariate data, and that's the best way to deal with that one. Okay, let's see. One more. We have time for one more. Another one from Denise. Most drugs exhibit formation rate limited metabolite kinetics. Yeah, in some cases. In this case, how do we interpret the results that we get from NONMEM output when dealing with a metabolite in which we had to make simplifications, either fraction metabolized as 1 or fixed volume distribution? What does our elimination rate constant for the metabolite tell us? Can we deduce anything about what type of metabolite kinetics we have, formation rate limited or elimination rate limited, based on our output? Okay, so that's why you're interested in the rate constant, is this determination of formation rate limited or elimination rate limited by comparing the magnitude of the rate constants. The fraction metabolized is going to impact the formation of the metabolite. the elimination will be estimated relative to that fraction as well. Can we still make inferences about formation rate limited or elimination rate limited based on our output? Yeah, and I think you can. I think you can derive a rate constant, which is going to be just that scale between volume and clearance, and then compare that to the formation rate constant. But without knowledge of what that formation fraction is, this is a good question. I'll get back to you on that one, Denise. I think my first hunch here is that you can still look at that rate constant and have some idea relative to the transformation of parent. Because remember, we're fixing the fraction metabolized, so that's the amount, and so we're changing the clearance, but we're not necessarily changing the rate constant if you were looking at it as a first order process. So the rate constant from parent to metabolite could be compared to the rate constant from metabolite out. And in that case, if you had a much slower rate constant for elimination of the metabolite, you could still conclude elimination rate limited rather than formation rate limited kinetics. Tough question. Okay, so we're at the end of the hour here. Let's, I'll try to keep up with some other questions, but I think we've done a good job of knocking out most of the discussion board questions. If there's one that I've missed and you really want an answer, just post it again, please, or remind me what the question is, and I'll get back to it. Sometimes they do come across in quite a flurry here, and they do fall between the cracks, so I apologize for that. But thanks for your interest. I really like to see the enthusiasm, and I also love it when the group here is helping each other out and answering questions too. That's great to have that sort of a community discussion going on in this class site. Anyway, that's a wrap for today then. We'll pick it up again on Tuesday with some more advanced PKPD modeling. I hope you all enjoy the weekend, and we'll talk to you then. Thanks a lot.